Okay, so now that we've learned all about DC motors and we applied them to lift boxes of bricks and stuff like that, now we want to talk about using electric motors for electric vehicles. So this is what we're going to end up be doing for our next project. So we're going to be looking at the uh, model Tesla 3. The Tesla 3 is the one that's a little bit more reasonably priced. So in order to look at this, we're going to start by watching a little video that shows somebody showing off their Tesla 3. So we will watch this YouTube video. Now we're not going to watch this whole video right here, but you can watch it later if you want. So
what's up, you guys? So today I am in the Tesla Model 3 Performance, and we're just gonna have a little fun. I'm gonna pick up some friends, and I'm gonna show them what this thing can do.
Like park and drive and stuff like that.
So drive, you just push down like that.
This is crazy.
Yeah, it's pretty cool.
Oh my gosh, I feel like I'm in like a spaceship.
Yeah, dude, it's pretty cool.
Oh! Whoa! Whoa, we went really fast. Whoa. I was not ready for that. Does this go really fast?
Yeah.
Oh, yeah, it does. Oh my gosh, this is so cool. Whoa.
Hey, try to touch this.
Whoa!
Dude, you have romantic.
okay, so you can kind of see that the advantages that you have with these electric vehicles is the fast acceleration, stuff like that, that comes with the electric motors. Like we've been talking about, the DC electric motor has its uh, highest torque at start, so they have very fast accelerations. So just to look at some of the specifications on this that we'll be looking at and using is, so the model Tesla 3, and just for comparison, I put on my Toyota Corolla down here at the bottom so you can kind of see some comparisons. So the Tesla 3 is 1,800 kilograms is the weight. My Corolla is 1,200. So you see, first of all, that the Tesla is a lot heavier than my Corolla is. And typically, if you would assume that heavier it is, the slower it's going to accelerate because then it's going to have more moment of inertia and more mass, harder to accelerate. You can also see some of these drag coefficients, cross-sectional areas, and we'll talk about all that kind of stuff. But you can kind of see the drag coefficient in the area for the two cars are, fairly similar. The 0 to 60 for the Tesla is 3.2 seconds compared to my brand new Corolla, which is 8.2 seconds. So 8.2 compared to 3.2, I would say the 3.2 is way faster acceleration than my Corolla. It also has a top speed that's a lot higher. Now, obviously, the Tesla 3 is a lot more expensive than my Corolla, but you can kind of get the idea here. So we need to talk a little bit about how do you model the acceleration and the maximum speed and all of that stuff for an electric vehicle. So we want to look at the forces that are on the car. So first of all, we have this aerodynamic drag right here. So the aerodynamic drag is as the car accelerates, it has to move all of the air out of the way, and so the air pushing on the car is going to slow everything down. We also have what's called this rolling resistance, and that's basically just the friction that you have between the tires and the road. Now you also have, if you're going up a hill, you basically are changing your potential energy, so you have this force going, which is called this hill climbing force. When we do our project, we're not going to worry about this hill climbing force. We're going to be on a flat surface. And then the last part, so these are all of the forces that pull against the car. The last force is the motor, right? So this is put in terms of torque and instead of in terms of force. And so then this is the motor that it's applying to accelerate the car forward. So let's look at these forces that go against you. So starting with the aerodynamic drag. So this is the force needed to move the air out of the way. So here is the basic equation that we have for the aerodynamic force. So we have the CD is your drag coefficient. And so that's kind of how easy it is for the air to flow around the vehicle. The A right here is the cross-sectional area. Obviously, the bigger the cross-sectional area, the more force you're going to get. This is the air density. So if there's less air, there's less force, and so you're going to have less drag. And then what we see here is the aerodynamic force is going to be proportional to the velocity squared. So this is similar to when we were doing fans and blowers and stuff like that. The faster you go, the more force you get. The rolling resistance, this is a function of the friction of the tires on the ground. So it's basically going to be your friction, your rolling friction coefficient times the force of the car on the ground. So it's basically just going to be this coefficient times the weight times the gravity constant. And you see that this force is completely independent of the speed. So it doesn't matter if you're going slow or fast. This one's going to be independent of the speed. And you can see that this friction coefficient depends on the type of tires and how much pressure you have and all that other stuff. And you can see these are tires on concrete. You know, if you're going through the sand, obviously your friction coefficient is way higher. So you get a range here. And then the hill climbing force is basically just going to be related to the angle, what the force is that is against the direction that you're going. So now if we want to analyze the acceleration, well, we have two things. We can either take all of our forces and convert them into torque and do our net torque and our moment of inertia like we've been doing before, or we can convert the torque into a force, and then you basically just have your mass times acceleration like we're used to using in physics. So I think in this one we're probably going to convert everything into force, and so rather than converting the forces into torque, we're going to take the torque of our motor and convert it back into the force on the vehicle, which is basically just going to be the torque of the motor divided by the radius of the tire. Now this is the torque that's actually applied to the wheel after any gear ratios, gearboxes, and all that kind of stuff. In this project, we're basically just going to assume, we're just going to calculate the torque to the motor and not worry about the gears and all of that kind of stuff. So now what we see here is our basic equation right here is just going to be the mass times the acceleration is going to be equal to the sum of the forces. So we have the engine force minus all of our drag forces here. Now in our electric car project, what we're going to be doing is we're going to be determining the DC motor needed to attain these specifications. Now the actual motor that they use is an AC motor and not a DC motor because AC motors are more efficient. But the DC motor is easier to model, so we're going to analyze the DC motor to make the problem a little bit easier to find. So what are our main design parameters? So our main design parameters, as we've kind of been playing around with, is our series resistance and the torque and back EMF coefficients. And we're just going to set them equal using the units. As we found out from the specs, they're pretty close to being equal for most of these cases. So we basically have two parameters that we're going to be adjusting, and our main performance specs are going to be our 0 to 60 acceleration and our maximum speed. So we have two unknowns and we have two equations, and we have to solve those. The problem is that solving these equations aren't analytic equations, they're differential equations. So what we're going to have to do is we're going to have to model these in Simulink, and then we're going to be adjusting these parameters until we meet these specs. And that's what we're going to be doing for the next project, playing around with Simulink and motor parameters, and it kind of ties all the stuff together that we have been doing.